Good afternoon, everyone. My name is Tommaso Melodia, professor at Northeastern University. Welcome to our webinar. We're going to talk about Colosseum, large-scale programmable wireless emulator for the research community. So what is Colosseum? Well, you may have an idea if you're here, but Colosseum is a massive $20 million wireless system testbed that's been developed by DARPA to support the Spectrum Collaboration Challenge. Colosseum in its previous life has resided at the Johns Hopkins Applied Physics Lab. The team at Johns Hopkins Applied Physics Lab has played a key role in developing Colosseum and also in operationalizing it during the Spectrum Collaboration Challenge. After the challenge was over, Colosseum was transferred to Northeastern University in November 2019. As of today, Colosseum is up, operational, and open to the NSF community. The transfer to Northeastern has been supported by DARPA and by a grant, a CCRI grant from the National Science Foundation, which we gratefully acknowledge. Through this grant, Colosseum joins the ecosystem of NSF-funded platform for advanced wireless research, wireless testbeds. POWER, or PAWR, is a public-private partnership, $50 million committed by the National Science Foundation and $50 million committed by a consortium of industries to develop 4 city-scale for advanced wireless research. Together with the POWER platforms, Colosseum will support remote shared access, research in 5G, softwareization, slicing, security, Open RAN, the area of spectrum sharing, finding new ways for different wireless technologies to share the same portions of the wireless spectrum, work at the intersection between artificial intelligence and wireless, which is the original purpose that Colosseum was designed for, and work in the area of Internet of Things in general. Plus, whatever the research community will find valuable to investigate over Colosseum. What is Colosseum? From a hardware perspective, in terms of highlights, Colosseum is known as the world's largest wireless emulator, but I'm going to show in this webinar, together with my colleagues that will talk after me, that Colosseum is really much more than a channel emulator. From a hardware perspective, it's composed of 256 USRP X310 software-defined radios. Our community is very familiar with them. They're fully programmable. Each one has 2 front ends that operate between 0 and 6 gigahertz. It has a fabric of field programmable gate arrays, programmable hardware that emulates in real time the 65,000 wireless channels that exist between each pair of USRP radios. There's 128 servers with GPU that are remotely available for user experimentation, a number of scenarios for better generalization of machine learning models. It provides large-scale experimentation of wireless RF systems with spectrum in the loop. As you see in this nice illustration, which we inherited from DARPA here on the right, Colosseum can create virtual worlds and help us understand the interactions of wireless radios and transceivers in these virtual worlds. A little more detail, Colosseum has 256 USRP X310, as I mentioned. 128 are used as user devices. 128 are part of the Colosseum Massive Channel Emulator, or MCAM. There's 65,000 channel, 65,100 megahertz emulated RF channels. We have 21 racks of radios, high-performance servers with CPUs and GPUs. Provides full mesh networking capabilities. It has massive computing and support resources of its fabric of FPGAs, GPUs, and CPUs, 900 terabytes of network attached storage, and we're also working to increase that, 320 FPGAs, 18 10 gigabit switches, 25 clock distribution system, and it generates 52 terabits per second of digital RF data, terabytes, sorry. You can look at this nice time lapse that shows the day when Colosseum arrived at Northeastern University. I'm going to go through a little bit of the architecture. At the center, what you see here is the RF emulation system, which is composed of FPGAs that emulate in real time the wireless channels. The RF emulation system is connected to the so-called standard radio nodes. The standard radio nodes, which are referred to as competitor system. The competitor is a term, a legacy term that we inherited from DARPA, which used Colosseum for a competition. So you can think of this as a user system in terms that are more familiar to the research community. So the standard radio nodes comprises a server, compute node, an SDR connected to the server, and a container, a virtualized container that includes all the software that is used for the system. And each SDR is associated with one container. There is a traffic network, a traffic generation system that can generate traffic for the entire system and send it to the various nodes. And there is a system, so-called competitor website, through which users can access the system, schedule access to resources, and things like that. So Colosseum, just to give a sense, it's much more than a supercomputer, though. It's not only in a simulation environment. It has, as I mentioned, RF hardware in the loop, and that differentiates it from a number of supercomputers that can provide very complex wireless simulations. It provides real-time emulation with real signals and emulated channels. And it combines in a single instrument the fidelity of hardware channel emulators, the flexibility of a virtualized data center. All the software stacks that are executed on the radios are virtualized. And the scalability of a network simulator, so with up to 256 independent radios. It's fully programmable. It was, as I mentioned earlier, a 20 million plus investment by DARPA. As of now, there's a $6 million investment by the National Science Foundation and an additional $2 million investment by Northeastern to renovate and operationalize the rooms where, where Colosseum resides. Colosseum combines massive RF hardware and programmable hardware to emulate in real time the complex RF scenarios. You can think of scenarios including spectrum sharing, radar, etc. The complex hardware in the loop emulations available to Colosseum are not possible with existing simulation models, and transmissions are generated by real programmable hardware. So this is what the massive channel emulator looks like. It emulates in real time the channel between the 256 independent transmitters. And each channel is based on a 512 tap model, which is, however, implemented because of the computational limitations as a sparse channel. So only 4 of the 512 taps are non-zero. So the way this looks like, you have the USRP X310, which you see here in the left in the user space, that are connected to USRPs in the massive channel emulator. So the signal that is transmitted over a cable at radio frequencies down converted, resampled, and fed into the fabric of FPGAs that implements all the channels and then feeds back the signal, the baseband signal, to every receiver and sums the contribution from all the individual channels at each receiver. The scenarios, different scenarios, are implemented through a scenario server that contains the taps that characterize a specific scenario and the evolution in time of these taps. We'll get a lot more detail on this later in the webinar. This is what the standard radio node looks like. There's basically 3 components. One is the SDR, as I mentioned, is at X310 USRP. Then there is the server, the compute node. There's a bunch of Dell servers with each one with CPUs and a GPU. And there is a competitor software implemented as a Linux LXC container that is associated with an SDR, and that basically implements the software stack. Then there is cooperation with a number of other systems. We will go into more detail later in the webinar. There is a traffic generator. Traffic generator can create UDP traffic flows between the software radios, the standard radio nodes, and each basically traffic generator instances can be generated by means of Docker containers and associated, routed to each standard radio nodes, so as to create a complex complex traffic patterns. You can also generate traffic directly in the standard radio nodes, depending on what makes sense for you. Experiment workflow. What you see here, users can access Colosseum through the Colosseum website and create interactive reservations. So you can put an emulation job in the system, and there is an experimenter queue that can prioritize jobs between the different users of the system and schedule them at a time where resources are available. There's also the possibility of using Colosseum in the so-called interactive mode, in which a user just accesses an interactive session, reserves some resources, for example, certain standard radio nodes, and can do experiments in an interactive mode. This is what we're going to talk quite a bit about the concept of scenario in Colosseum. This is a scenario that we inherited from DARPA called Alice of Austin. Basically, the scenario includes basically a number of nodes that coexist in the wireless channel, the variation of position of the nodes in time, traffic scenarios, and RF taps and their evolution in time between all the nodes in the system. There is a notion of something called scenario conductor in Colosseum. The scenario conductor is an entity that schedules different reservations on different portions of the MCAM system. So you have various transmission channels and reception channels that can be mapped to a specific experiment by the scenario conductor, so that you can in parallel have multiple experiments being conducted in Colosseum in the same hardware fabric. So that makes it a very powerful system here. Colosseum, I wanted to mention, is ready to provide experimentation in softwareized cellular systems in Open RAN. For example, Colosseum has 5G capabilities in terms of instantiating cellular networks with SRS-LTE, while the current version of SRS-LTE is not fully 5G compliant yet, but it will become in the next few months. And you can emulate scenarios in which, for example, you have 6 interfering base stations with 24 users that can be associated with the various base stations, with downlink video streaming, user mobility, and the like. We have created a number of scenarios. One scenario that will be made available to the community is the scenario of the area of Rome, Italy, next to the actual Colosseum. So we had a Colosseum scenario in Colosseum, which we thought was an interesting proposition. Additional Colosseum 5G scenarios that are being developed. We're going to have one of the Boston Public Garden and a scenario of the Powder PAWR platform in Salt Lake City, Utah. We wanted to mention that, and this is something, again, that will be discussed at length later in this webinar. Colosseum works in a fully virtualized environment. So when you generate your complex software stack with non-trivial algorithmic components in Colosseum, you can test at scale in an emulated scenario, in a fully reproducible and controllable scenario. You can then move your experiment, for example, in a real wireless testbed, maybe a wireless testbed that you have at your own institution, smaller scale or larger scale. For example, we move experiments from Colosseum to our own arena testbed, which is an indoor testbed with 64 antennas at Northeastern University. And then you can take the same container and test at large scale over some of the Power platforms that are already available, like Powder or Cosmos or AirPaw in North Carolina, which will soon become available. Colosseum will be serving different communities. It certainly will be serving the US academic community supported by the National Science Foundation and operating parallel with the Power Project Office. Colosseum will serve the DoD S&T community at the unclassified or ITAR restricted level. Colosseum will also be serving the DoD S&T community for classified research. This is something that is not available yet as of today, but it's on our timeline. And it will be a resource for industry to innovate in the wireless area and in the area of 5G. So everybody is welcome in different ways. NSF-supported researchers can access Colosseum free of charge as of today. We will provide basic support and documentation. We will provide scenario creation on a best effort basis. So the idea is you are researchers, you can tell us what you're trying to accomplish. We will try to direct you to an existing scenario if there exists that can help you experiment with your ideas. Or if that scenario doesn't exist, we will try to work with you to develop a new one. Of course, our resources are limited, so this will be provided on a best effort basis, but we're committed to enriching the set of scenarios that based on demand from the research community. DoD researchers supported by ARL, AFRL, and NRL can access Colosseum free of charge for 2 years. Industry and other researchers are welcome to talk to us, connect to us through colosseum@northeastern.edu. We are developing a fee structure for use by communities of researchers that are not currently contributing to the Colosseum operations. How do you get started with Colosseum? Well, we ask PIs to submit a new team request through colosseum.net. Colosseum.net is the new Colosseum website. You'll find the form to request a new team under the useful links. PIs need to be either supported by NSF or be a DoD researcher, as, for example, AFRL, ARL, and NRL, to request a new team through this route. And again, if you don't fall into one of these categories, you can still use Colosseum, but it will not be free of charge. So you can connect through colosseum@northeastern.edu. What are we thinking in terms of the evolution of Colosseum? Colosseum, as of today, provides 256 by 256 mesh for sub-6 gigahertz research. As of today, we can support scenarios in areas that are 1 kilometer by 1 kilometer with omnidirectional transmissions. We have received support by the from the National Science Foundation through the NRDC program to extend the capabilities of Colosseum to create an additional 13 by 13 mesh that will have extended capabilities in terms of supporting scenarios that are 100 kilometer by 100 kilometer. And we'll also be developing a millimeter wave quadrant for Colosseum, which will include a 16 by 16 mesh with millimeter wave directional propagation in the scenarios that are 1 kilometer by 1 kilometer at most. So stay tuned. These capabilities don't exist as of today. This NRDC and millimeter wave capabilities, but will become available in the future with Colosseum. That's on our roadmap. And we will also be enhancing Colosseum with additional supercomputing power, with a significant amount of supercomputing power. Stay tuned, we will announce that soon. The agenda for today, the next portion of the webinar will include the Colosseum use cases. Then we will have a session on from Colosseum to Power. We'll have a break between 1 and 1:10 p.m. Then we'll talk about Colosseum scenarios and traffic, how to use Colosseum for first-time users, how to create a container, and then Colosseum events and community. Last, I'd like to acknowledge the team of CoPIs. Without them, Colosseum will probably be sitting in a room as of today, and nobody will be able to use them. Like to acknowledge Kaushik Chaudhary, Stefano Basagni, and Manu Gosain provided fantastic support, and you'll hear from them later in this webinar. And also, I'd like to acknowledge all the people that are making this possible. It's a large group of people. There's the Northeastern team, Leonardo Bonati, PhD student. Nobody knows as much about Colosseum as he does. Salvatore Doro, Pedram Johari, Francesco Restuccia, Subramoy Mohanty, Mihad Montasce, Michele Polese, Ahmed Ali, Sweta Srivastava, and Fiona Morgan. The team from Servo.io, which is a company that is helping us manage the Colosseum infrastructure, the network, the cloud functionalities, everything that has to do with infrastructure is being managed by them. Michael Seltzer, Ajit Baga, Ben Spetkov, and Paresh Patel. And Kurt Yoder, who is a consultant for us. Kurt Yoder has been absolutely instrumental in the transition. He's the memory of Colosseum because he worked with the APL team in Colosseum's previous life. Without his help, we would still be trying to figure out how to turn it on. I hope this helps understand what we're going to be trying to do with the rest of this webinar. For any questions related with Colosseum operations, please email colosseumhelp@northeastern.edu. For programmatic questions and how to use Colosseum, you can email colosseum@northeastern.edu. Thank you.